So yes, we talked about linear transformations. We also talked about systems of linear equations, right? So what's a system of linear equations? We talked about two views that we could take of a system of linear equations, what it means to solve a system of linear equations. So what does it mean to solve a system like this system? Let me erase this from another section here. So we had the so-called row view, and then we had the so-called column view, right? So let me copy the system. What did we mean by that? How did we write down the system?
Column view is when you write the system as a matrix, just by a matrix of the coefficients, and then you multiply it by x, y, z, or like whatever variables the coefficients are associated with.
Yes, so that x stands for, in this case, let's say x1, x2, x3. So it could be x, y, z. Okay, x1, x2, x3. And then you have this matrix A. Well, that's just a way of writing it down. It's not yet a column view. It's not yet what we call the column view. So let's talk about that now. So you have this matrix, right? So the matrix looks like 1, 1, 1, 2, 5, minus 1, minus 1, 0, 2. So this way, so matrix times a vector of x equals 4, 11, minus 3, right? So this is a shorthand way of writing down the system of equations. The column view tells me that if I were to take x1 times the first column of A, which is 1, 2, minus 1, if I were to take x2 times the second column of A, which is 1, 5, 0, and then add to this x3 times the third column of A, which is 1, minus 1, and 2, I would get exactly the right-hand side, 4, 11, and minus 3. How did we imagine this geometrically?
You graph the vectors of each, like of the matrices, like next to x1, x2, and x3, and then you add them together. So like it geometrically, it like stretches out and stuff.
Yes, that's exactly right. So let's just do this just to make sure everybody's on the same page. So let's suppose this is like the blue vector. Let's make this one like a green vector, and let's make this one like a red vector. So the red vector is, so let's say that this is x1, this is x2, let's say this is x3. So, all right, let's start with blue vector, whatever. 1, 2, minus 1, 1, 2, minus 1, point somewhere here. It's kind of hard to draw, but you get the idea. It's points down below that x1, x2 plane. Then you have the green vector. This green vector is 1, 5, 0, 1, 5, and then 0. So it goes like this way. And then you have 1, minus 1, and 2, the red vector. 1, minus 1, 1, minus 1, rather, this way. 1, minus 1, and 2. So that guy goes that way. So you have these three vectors here in three-dimensional space. Okay. And you have the right-hand side vector. Let's make this guy, I don't know, purple. So this guy B is purple. So B is 4, 11. This 11 is up here, and then minus 3. So it goes like down here somewhere. So you have this purple vector. So what this column view says is that how much I should stretch the green vector. This is the stretch factor is going to be, for the green vector, it's going to be x2. How much should I stretch the blue vector? That's the stretch factor here, x1 for the blue vector. And the stretch factor for the red vector is x3. Now this stretch factor can be like shrinking the vector too. So if it so ends up that the solution to this system of equations is such x1, x2, x3, in which like x3 is like 1/2, for example, it means that I'm shrinking the red vector twice, not stretching it, but shrinking it. Also, those coefficients can be negative, which means that I'm reversing the direction of the vector. But either way, what I'm looking for is what combination, and what did we call this combination? A linear combination. Linear combination of the column vectors of A column vectors of A, okay, what linear combination of the column vectors of A gives me B? Gives B. Is this what you explained to us just a few minutes ago, right? Okay, is everyone on the same page with this? This is the column view of the system. Now, what was the row view? We did have nice pictures with like these colorful planes and so on. An alternative view. This row view, by the way, we found it very convenient to have this row. So we'll prefer the column view and what's to come. But the row view, like today, we'll talk a little bit more with the row view when we'll talk about Gaussian elimination. In the row view, we talked about a bunch of planes. Where did the planes come from? What are the planes? So here's a system of equations. In one of the slides, we actually have the pictures. I'll switch to that slide in a second. But first, please remind me. So what is this first row? Again, we're at the row view. What does the first row tell me?
It gives you the equation of one of the planes.
Yeah,
so like x1, x2, x3 equals 4 is a plane.
Yeah, this first line may be one of those like planes. The second line or the second equation may be this other plane. So they usually intersect at like along a line. It's possible to sometimes get parallel planes. This is what the two equations give you. And then the third plane comes in. And again, usually it will intersect the two other planes in just 1 point, exactly 1 point. That will be the single solution. This geometric view, like without doing a lick of algebra, from this geometric view, the row view, we made an observation that there's no way you can have a system that has 17 solutions. There's no way you can have a system that has 22 solutions. A system will either have exactly one solution, or it will have no solutions, or it will have an infinite number of solutions. These are the only possibilities. And that we did without thinking of algebra at all. It's just from these geometric considerations. Now, today we'll do some algebra, and we'll talk about the method of Gaussian elimination. Okay, so it's called the method of Gaussian elimination, but the method was known in the 3rd century BC by the Chinese mathematicians. Undoubtedly, it was rediscovered many times throughout the centuries. It was probably known by the Indian mathematicians. In the Middle East, it was known. By the time it reached Europe, if it did by the 12th century, who knows? But today it goes by the method of Gaussian elimination. And Gauss is the 19th century mathematician. So we'll talk actually not about the Gaussian method, but the Gauss-Jordan method. So that's the topic of today. That is a systematic way. So that's like with a 3x3 system of equations, it's easy to see the solutions. Maybe not that easy. You kind of have to like imagine it, strain yourself, maybe do some algebra, but you can write down the solution to the system of 3 equations with 3 unknowns without having any systematic way, knowing about any systematic way of doing it. But what we'd like to know is we'd like to be able to solve systems that are 1,000 by 20,000 or 70,000 by 2 million. In a systematic way. We want to be able to tell the computer to solve it. We want to have a procedure that we know works. And that's the Gauss-Jordan method that we'll discuss today. Okay, so now what we'll do now is we'll find the actual x1, x2. By the way, can you guess which x1, x2, and x3 work? Can you guess? Maybe that's unfair. Well, I just did this in another section so that I kind of know because I did it in the other section.
Is it 1, 2, 1?
3, 1, 0 works. Right? If you stretch this vector 3 times, the blue vector 3 times, and add to it 1 times this blue vector, you'll get exactly the right-hand side vector, the gray vector, the purple vector, right? So you can check that this works algebraically. Now that's a solution. So 3, 1, 0 happens to be a solution. So we'll get to this solution in a minute. So let me erase this. So I'm about to erase this picture. It's not a bad picture, actually, compared to how I drew it in the other section. So let's just do it. So here's what we're going to do. Now, if you had to solve it, like if somebody gave you the system in middle school or high school, how would you do it? You'll just eliminate variables, right? If you had to solve it, you really would solve it. It's not that big of a deal. So for example, you could eliminate the variable x1. Okay. Now, this way of writing down the system, ax equals b, We want a kind of shorthand. We want to have a kind of shorthand that would allow us to not carry over these x's all the time. So what we do is we write down what's called an augmented system of equations. So I write down the matrix A. It's going to be here on the left side, like this. And by augmented, we mean we take matrix A and augment it with the right-hand side. That is, tack on the right-hand side vector to its right, and that we'll call that enhanced or augmented system. Okay, so 4, 11 minus 3 goes here. So as you can see, what I have here, this is the B part, and this is the A part. So A times A next to B, this matrix, which is now a 3x4 matrix. A used to be a 3x3 matrix. When I put it in another column next to it, it has just become a 3x4 matrix. Okay, good. So now we're going to be dealing with this augmented matrix in what's to come. I'm about to eliminate variable x1. How do I do this? Well, if I subtract 2 times row 1 from row 2, that is, let's make this a different color, like a purple. If I take row 2, and if I subtract 2 times row 1 from it, from this row, then I'll be left with, so you help me with what? I haven't changed the first row at all. I haven't changed yet the second row. Okay, later after you've done like a couple of these, if you haven't done them before, then maybe you'll do a few steps at the same time. But for now, we'll do it one step at a time. And you know what's coming, like in a few minutes, I'll be asking you, like, what is it exactly that I'm doing? Actually, let me just talk about this for a second. What we want to do is we want to transform this system somehow into a simpler looking system from which we can read off the solutions. So right now, if somebody asked me immediately what the solution is, although we guessed it a few minutes ago when we looked at the column view, just by looking at the system, like if it's the first time you're seeing it, it's kind of difficult to guess what the solution is. But if the system were much simpler looking, like if the system were this, x1 equals 5, like it's a completely different system. X2 equals 7 and x3 equals minus 37. What's the solution to this? First of all, what's the matrix that corresponds to this system? What's the AX equals B here? This is a different system, but what is A?
Wouldn't A just be the matrix of like 1, 0, 0, 0, 1, 0, 0, 0, 1?
Did you mean this one?
Yeah.
Okay, yeah, that's exactly what it would be. We'll call this an identity matrix, and we'll have a special notation for it. Well, X here, and the right-hand side is whatever it is, 5, 7, minus 37. So what's the solution to this system of equations? That's our system.
Your x1 would be, so your x1, x2, and x3 for your column to the right of the identity matrix, that would just be 5, 7, negative 37.
Yeah, that's the solution. So we immediately see the solution, right? It just, the matrix, the way the system is written down, it just gives me the solution. So it tells me what the solution is. So with this system, it's much more difficult to tell. So what we're trying to do is we're trying to bring this system into the simplest form that we can. Okay, in this case, this is our first example, and we'll actually get lucky because the way the numbers were selected, we'll actually get it down to an identity matrix, just like this. We'll get to something, our right-hand side will be different, but we'll get to something like this in a minute. In fact, our right-hand side will end up being 3, 1, and 0. How do I know? Because we just wrote down the solution when we had the column view. I know that the solution was going to end up being 1, 3, 1, 0. And that's what we'll end up seeing in a few minutes. But as of right now, we don't know. We don't know. What we're doing is we're transforming this original system, this augmented form, into a simpler form. And we're doing this by carrying out the so-called allowed row operations, legitimate row operations. Why are they called legitimate? Because they don't change the solution set. And I'll be asking you, in fact, what makes me so certain that these operations do not change the solution set? Well, then you ask, well, okay, so I'll think about it, but what are the operations? And the operations are these. There are only 3 allowed operations. Okay, let's start with the first one, probably the more involved one, which says an allowed operation, one of the allowed operations is take any row and add to it a multiple of another row. Apparently, this procedure, like take a row and add to it a multiple of another row, like here, we took row 2 and added to it minus 2 times row 1, okay, a multiple of another row, that didn't change the solution set. What exactly do I mean by this? Well, whatever x1, x2, x3 satisfied this system of equations, exactly that set of x1, x2, x3s satisfies this new set of equations. Okay, and I haven't added any new solutions as I perform this operation. Take row, one of those rows, and add another row. Okay, so more about this as we go along. For now, what is my second? We don't even have the second row written down yet. So what is my second row going to be? What I'm doing is I'm replacing the second row with whatever the second row was plus a multiple of the first row. In this case, a multiple is twice the first row with a minus sign, so that I get a 0 here. That's the whole idea. So how did I get a 0 there in that position? To get a 0, I subtract twice row 1 from the second row. So what do I get here? Do I get a 3 here? Let's use a different color. Let's keep this color. Right? Am I correct? Okay, so is this what I get? Just let's make sure that everybody sees what I just did. I took this second row, row 2, minus 2 times row 1. So 2x1 plus 5x minus x3 equals 11, and minus 2 times x1 plus x2 plus x3 equals 4. And when I added those two up, I got a 0 times x1 here, plus 3 times x2 here, minus 3 times x3 here, equals 3 here. Right? And that's what I wrote down here. Okay? Does that make sense? Did everybody sign in? How many people are actually present right now of those logged in?
Yeah, I just have a quick question, Professor.
Yes, please.
How did we get the 0 at 1, 4 in that matrix all the way to the right?
Oh, that's because I made a mistake here. No, we didn't. I just
Right, yeah,
rewrite that row.
uh-huh.
Yeah, that row, just rewrote that row.
Got it.
Okay, so it's clear how we got here, right? Now let's continue. Now I'd like to make a 0 in this position. How do I make a 0 in this position? Let me erase this so that I have space. Nobody has any questions about this, right? So I'm just going to erase this. And now I want to get a 0 in this position. How do I get a 0 in that position?
Add row 1.
Yeah. So add row, did you say add row 1?
Yeah.
Yeah. So just add row 1 to row 3. The way I'm going to write down, notice that row 3, this is what I write down first, the row that I'm manipulating. Here I was manipulating row 2. So you started row, you're replacing row 2. This one goes here first in this notation. Row 3, plus row 1. So this is going to be like that. This is going to be 0, 1, 3, and 1. Am I correct? So I just added row 1 to row 3, and I replaced row 3 by it. Okay, so now notice that as we go along, what I'm claiming is that as I'm doing this row something plus a multiple of another row, I'm not changing the solution set. Also, I'm not changing the solution set if I multiply any of these rows by a number. So for example, if I take the second row and multiply it by some number, like 1/3, I'm not going to change anything. I'm not going to introduce any new solutions, or I'm not going to take away any solutions that the system just before had. I'll be asking you why in a second. 1, 1, 1, 4, 0, 1, minus 1, 1, and 0, 1, 3, 1. This is my solution set, my system of equations, right? Okay, so what do I do next? What's my next step?
you want to make sure make sure anything below the second row is so the anything below that one in the middle row, you want that to be 0.
Yes, that's exactly where we had it. So this is our main diagonal of the system of the matrix. Everything below the main diagonal, I want to make that 0. So I want to make a 0 here. So how do I make a 0 there? So let me rewrite the top row. Let me rewrite the second row. And now I'm making a 0 there. So how can I do this? I have to,
yeah, subtract the second row from the third row.
Yeah, if you subtract the second row from the third row, you get exactly this, right? Okay, so I've subtracted the second row from the row. Now, what we have is that, like right now, if you were in a hurry, you'd write down the solution by using the back substitution, right? Because the last equation tells you that 4x3 is 0, from which you get that x3 equals 0, right? So you take that x3 equals 0, that's the solution. It's like the third component of the solution of the x vector. You take that x3 and plug it into equation 2, so that you get, when you see that it's x2 minus x3 equals 1, well, that x3, that equals 0 from here. So you get that x2 equals 1. So that's the second component of the solution. Then you plug whatever you have into the first equation, which says that x1 plus x2 plus x3 equals 4. But of course, x3 you know already is 0. You know x2 is 1. So what you end up with is that x3 equals 3. And that's, if you remember, like a few minutes ago, that's exactly the solution. But we're not going to do it this way. Yes, we know what the solution is, but we are after a method, not just a solution. So what we're going to do is we're going to just forget about the solution. Let me put it here so that make sure we get the same solution at the end of the day. Just let's put it here. Let's continue with the method itself. The method itself goes on to do the following. It wants ones on the diagonal. So, okay, remember our goal is to get to the identity matrix. So it wants ones on the diagonal and above the diagonal also, not just below the diagonal, but above the diagonal as well. It wants to put all the zeros. Okay. In a few minutes, I'll be asking you under what conditions is that possible, or when is it impossible? When can this procedure go wrong? But for now, in this example, we'll be able to put zeros here in those positions without changing the solution set. So let's go on and do that. So first things first, I think I can divide the third row, taking it one step at a time, by 4. When I do that, I rewrite the first row, haven't done anything to it. I rewrite the second row, haven't done anything to it. And the fourth row becomes this. I divided the fourth row by 4. I can continue. Now I want to make a 0 in this position. How do I do that? So I'm manipulating, what should I write here? I'm manipulating row 2 and some other row. This time, this some other row will be a row that's below row 2. So row 2, what should I do to row 2? In order to get a 0 there, the third row isn't going to change. The first row, I'm not doing anything to yet. But in the third row, I want to get a 0 here. In the second row, I want to get a 0 here. So how do I do that?
Add row 3.
Yeah, if I add row 3, that's exactly what will happen, is I'm going to have this row 2 change to what I just wrote. Am I correct? Am I correct, or did I make a mistake? Now, I think I'm correct, so let's continue. Now, what's the next step? I have 2 more steps left. Now I want to make a 0 here. How do I make a 0 there? I rewrite the third row. I rewrite the second row. And what do I do with the first row? What do I do with the first row? Please help me out.
You subtract the first row with the second row?
Yeah, exactly. I'm sorry, one more time.
Would you just subtract the first row with the second row?
Okay, so if I did that, would I get a 0 here?
Oh, you want to, you want to subtract it from the third row then?
Yeah, so what I want to do is I want to add -1 times 3 row, that is subtract the third row, as you said, from the first row. So let's write it down. So I'm going to take the first row and subtract the third row from it. Not the second row. It's important because if I subtract the second row from it, I will get a 0 in this position, and here I'm going to have a -1. Does that make sense? Why I'm not
Yeah.
subtracting the second row? Okay, so what we have is 0, not 0. What we have is 1, 0, 0, and here I have a 4. That's not correct. What I have is 1, 1, 0, and here I have a 4. Okay, and we have one final step left. What should I make to have just zeros above the main diagonal? That is only one entry, only that I want to be 0 is non-zero right now. How do I make that one 0?
Subtract the second row from the first.
Yeah, so I'm leaving the second and the third rows alone this time, and I'm subtracting, as you've just told us, the second row from the first, and I'll get exactly this by subtracting the second row from the first. And that's going to be in the form that we just want. This is my identity matrix augmented with some new B on the right-hand side. So I started out with this A augmented with B, right-hand side. This is the matrix with which we started. So let's start it here, start. And we ended up with this and with this. So what happens is that once we end up with that form of the system of equations, we do have a solution that's easy to read just from the entries. It just tells me that this x3, 1 times x3 equals 0. So what does x3 have to be? x3 has to be 0. There's no other way. The second row tells me that 1 times x2 has to be equal to 1. I'm not doing any back substitution or any of that funky stuff anymore. I just read off the solutions from the system, from the system that I get. So x2 must equal 1. Here it is. And x3, I can't believe this is x3 here. This should be x1. Okay. Should be x1. That x1 equals 3. So I read off that solution there. All right, does that make sense? So now we have a solution. This is an example of solving a system of linear equations using Gauss-Jordan elimination. Now, at this point, if you haven't done this before, you might have tons of questions. Like, what ensures that the solution that I get in the end, the guy that I read off the final version of the system, the simplified version, is exactly the same as what I had before? What ensures that I didn't change along the way as I was carrying out these steps? I somehow didn't change the solution. That's question number 1. And question number 2 is, what can possibly go wrong? Like, I did end up with a nice identity matrix here and some right-hand side there. But when we discussed the geometric view of the system of linear equations, so we had a 3x3 system, we sort of said, like, well, yeah, you can have a unique solution. And by the way, this is the case when we have a unique solution, but not necessarily. It may so happen that we have an infinite solution set, or we have no solutions at all. So what could have happened along the way for us to get no solution? Or to get infinitely many solutions? Any ideas?
Would you, when you're doing the row
Matrices,
operations, you'd get a row of zeros?
All
Yes.
will be 0.
Sorry?
All will be 0.
Yeah, so let's look at these couple of examples here. So this is our last step. This matrix here, this is the final step that we got here. This matrix is here. Well, this matrix, okay, from this we just read off the solutions. But it could have happened that our row, as we carried out these operations, became like something like this. Like you have a bunch of zeros and 8 on the right hand side. So what does this stand for? This row stands for 0 times x1 plus 0 times x2 plus 0 times x3 equals 8. Right? Are there any x's that satisfy this? Is there a way to pick up x's that satisfy this equation here? No way, right? There are no such x's. So what this means that if you get a row of zeros like this and the right hand side is non-zero, that means that's exactly the situation where we had these parallel planes. We had no solution to the system. If you remember the picture, the row picture here, parallel planes, that's the situation with the parallel planes here, wherever that was. Oh, it's on the other slides. Okay, so it's here. See the parallel planes? That's the situation with this setup. You could also, it's possible to get a setup where the right-hand side is 0. You get a bunch of zeros, but the right-hand side also becomes 0. In this case, what does this stand for? Which equation does this stand for? Does this have a solution? It has infinitely any x's you plug in, that's a solution. So what this means is that that third equation there that turned into a bunch of zeros didn't impose any new constraints to the system that we didn't already have with the first two equations. So it was a redundant equation, the third one. It gives no new information about how these variables x1, x2, and x3 should be related to one another and should be constrained. So in effect, you really have two equations that matter, the top two equations that matter. The third apparently didn't matter in the original system of equations. So now once you have this, now how many solutions does this have? So you have a system like, right?
It should be an infinite amount, right?
Yeah, it has an infinite number of solutions. Can you name like a couple of them?
X2 could be 1, x3 can be 1, and then you would find x1, which would be 1 minus 3 would be -2. So x1's -2, x2 and x3 are 1.
Yeah, what you just did, and that's fine, but you could have picked a different solution too, right? So the solution you gave us was a perfectly great solution, but I could have also picked x3 equals 2, then x2 would have been 0, and then if you plug in x3 equals 2, then you have 6 here, so 1 minus 6 is -5. So x1 equals -5. So this vector, -5, 0, 2, is a solution to this system of equations, as is the one that you told us about, right? What's the one that you gave us? You said x3 equals 1, x2 equals 1, okay? And then x1 equals -2, right? That's another solution to this system of equations. So in fact, you get to set x2, x3 to anything that you'd like freely. And then once you do, the other variables can be determined, right? It's given how you set the third variable. So that third variable is called a free variable. Okay, so tomorrow, the next lecture, we'll call the other guys pivot variables, when we'll actually write down the Gauss-Jordan elimination. This is just a preview of what's to come. Okay. So one last thing that I want to tell you about is, I want to talk about elementary matrices. These row operations, in effect, correspond to multiplying the original matrix A, what's called elementary matrices. Elementary matrices are matrices that have a lot of zeros in them, almost all of them, except for in like exactly one position outside of the main diagonal. So let me tell you what I mean by this. First, let me ask you this question. If I had a matrix like 1, 2, 3, 4, and if I simply wanted to, first let me ask you this. Okay, this is seemingly unrelated. I want to produce 1, 2 on this side. So the question is, what should I multiply this by from the left side so that when I carry out this product, and now you know how to multiply a row by a matrix, you know how to multiply matrices. This first row on the left is just a special, it's a matrix, it's a 1 by 2 matrix. But there is an easy way of thinking about this, right? Okay, so if I take this number and multiply it by the first row, and then add to it this number, the second row, the output will be this row. First, let's make sure that we're on the same page with what I said. This matrix, this blue matrix, is 1 by 2 matrix. When you multiply this 1 row by 2 matrix by a 2 by 2 matrix, what's the output going to be? Is it going to be 1 by 2? So dimensions agree. Row times, if you multiply a matrix by a row from the left, you get a row. If you take a matrix like this and multiply it on the right by a column, okay, you get on the other side, well, what do I get on the other side? So help me out. This is a 2 by 2 matrix. I multiply it by a 2 by 1 matrix. What do I get on the right side?
It's a 2 by 1.
Yeah, you get a column. It's a 2 by 1 column. So what should this column be so that, let's say, the right-hand side is 2, 4. What should be the entries here in this column? Again, remember how we multiply column-wise matrices. So remember our column view? What does this A times vector correspond to in the column view? It's some linear combination of the columns. Am I correct? So question mark, the first question mark times the first column plus the second question mark times the second column will give me, I want to get the second column. So if I make this question mark equal to 1 and this question mark equal to 0, if I multiply it like that, will I get exactly what I want? If you're still in doubt, you can do like the way you're used to with matrix multiplication. But my point, what I'm trying to do here is try to ask people to think of this matrix times vector as a procedure that manipulates the columns, in this case, of A, the columns of A. So then what this does is takes the 0 times the first column and adds to it 1 times the second column to get this. And if I multiply a matrix on the left like this by a row from the left, then I'm manipulating the rows of A. So for me to end up with 1, 2, what should the question marks be, please? Help me out. Can you help me out? Will this work? Am I saying that I should take 1 times row 1 and add to it 0 times row 2, and I'll get exactly the right-hand side there?
Yeah.
Okay. Now, if I say something like the following, if I had the second row here, okay, now I have a matrix. So now I have a second row. So let me lift this up. Now I'm multiplying a 2 by 2 matrix by a 2 by 2 matrix. And of course, on the right-hand side, I'm going to end up with a 2 by 2 matrix as a result. So I have some entries here. This row, when multiplied by the matrix from the left, will give me some entries here. What will these entries be? Well, they will be this element times this row plus this element times that row. When I add those two rows up, weighed by these two elements, I'll get the bottom row. The top row, I know what the top row is going to be. So help me out. What's the top row, please?
It's 1 and 2.
It's 1 and 2, because what this multiplication says here, this row times this matrix, we already know. This row times matrix says take 1 times the first row and add to it 0 times the third. So that's what you'll get. So now, if I wanted to subtract 3 times row 1 from row 2, what should these brown entries be? So I want to subtract 3 times, so help me out on this one. I want to subtract 3 times row 1 from row 2. So I take 1 times row 2, and I subtract 3 times row 1. Will I end up at 0 here? And a -2 here? So I'm thinking of this in terms of manipulating the rows. Now you could do the matrix multiplication as we always did before, element-wise. But my point is, like, there's really no need to do it. Let's think of it in terms of manipulating rows now. Okay, row times a matrix from the left is this row is kind of manipulating the rows of the matrix. Okay, so notice that I put a 0. When I put the 0 here, this is what we were doing with Gaussian elimination. We were trying to put the zeros below the diagonal. So the point I'm trying to make here is that the steps of Gaussian elimination, some row plus some multiple of another row, is equivalent to taking a matrix like this and multiplying it from the left by a special matrix. That's called an elementary matrix. So this matrix here is called an element. There's a notation that we use, it's called E. And this E has, this is actually called E21. And you say, why E21? Strange. Well, it's to E21 because this E matrix differs from the identity matrix I in position 2, 1, in the second row and the first column. So right here, right here. Otherwise, I'd have an identity matrix and zeros everywhere else. But this guy at position 2, 1, this entry is not a 0. It's something else. And that something else is, you know, how much do I have to multiply this first row by, and so that when I subtract it from the second row, I get a 0 here. That's what that E21 stands for. Does that make sense? So when I was carrying out all these multiplications here with the Gaussian eliminations, where was this? Like, where did we do this? Here, all these Gaussian eliminations here. When I did this multiplication, row 2 minus 2, row 1, can we kind of go out on a limb and say what 3 by 3 matrix did I multiply my original A by? Okay, so notice that I'm writing down like a bunch of entries. These are 3 by 3 matrix times a 3 by 3 matrix. Comes out a 3 by 3 matrix on the other side here. Okay. What should that, this is, my claim is this is an elementary matrix somehow multiplied by A and gives me like a new matrix. I call it A prime. Okay, so that the difference between A and A prime is that, well, the first row didn't change. The A's first row is the same. A's third row is the same. The only thing that changed is A's second row. And the way it changed, it just got a 0 here in this position by taking the second row minus 2 times first row, which is by doing this. So I guess the question I'm asking, like doing this, row 2 minus 2 times row 1 corresponds to which elementary matrix? Can I write it down with your help?
Yeah, would it be 1, 0, 0, then -2, 1, 0, and then 0,
Yeah.
0, 1?
That's exactly the point I was trying to make, and you made it before me. Okay. Now if you plug this in into, if you do by hand computation or plug it into a calculator, you'll get that this is correct. This multiplication produces exactly this right-hand side A prime matrix here as needed. In fact, when I carry out the second time, this row 3 plus row 1, I'll be multiplying both sides of this and that, multiplying again by another elementary matrix. So this was 2, 1. So which matrix? So help me out. This is the last thing of today. For me to get a 0 here, what am I doing really? What matrix? So
You're
here's my new
adding
matrix.
R3 and R1 to get the 0 there.
Yes, exactly. And what's the elementary matrix that, let's use a different color. Let's go with red here. So this E, what should that E be? And here's a claim, you tell me. So I'm multiplying the whole thing by this E.
It should be 1 0 0 0 1 0 and then 1 0 1.
Exactly, right? So are we on the same page? Like, does this make sense? If I multiply this whole thing by the matrix you just told us, which is here in red, I'll get, what matrix will I get? Will I get this matrix as a result?
You should, right?
Yes, exactly. And please verify it. So this is how we'll think about matrix multiplication from now on. It's just manipulating these rows of the original matrix. The purpose of these elementary matrices is to manipulate the rows of the original matrix. And now what's to come next? Now we're running out of time. These elementary matrices will help us to determine what, like, will help us talk about the inverse of a matrix.